Hello everyone, my name is Joshua Jacobs and today I'm going to be showing you some things in the Ansys application Fluent. This is the problem that we're going to be modeling. If you're interested in pausing, we're just going to be doing part 1, A through D. The first thing you want to go ahead and do is open up Workbench for Ansys. Next we want to find Fluid Flow, click and drag it into the system. You can go ahead and save. I don't know why this is giving me a hard time. Alright, now we're ready to get started. You can right click on geometry and open new design modeler geometry. This is going to open up one of Ansys's packages. We're doing a 2D flow, so you can click on the y-axis to make it 2D. We can change some of the settings to make it a bit easier to read. And now we can draw our rectangle. So you're going to go to draw, select rectangle, click on the origin, drag out a rectangle. It doesn't matter the size, we're going to dimension it. Select dimensions. You can click general, select this top line, drag out and select. We can go down here to H1. This is going to be the length of the flat plate. We're going to set it to 1 meter and click enter. Can select general again, and we want to select the right side, or we can do the left. And for the height, we're going to define it as 1/2 meter. This makes it much smaller, but if you right click and drag, we can zoom in. Next, we want to generate the surface. So we're going to go under concept, select surface from sketches. Now we select on the XY plane the sketch that we just created. We're going to hit apply. And generate. So that generates our surface. At this point, we want to save the project again, and we can close this. So now you'll see under geometry we have a check mark. That means that we're good, we have a surface, and we're ready to move on to the mesh. So open the meshing program by double clicking. Gonna give it a minute. So here's the surface that we just generated. You can go ahead and click again on the Z to turn it to a 2D problem. And the first thing we can do is just generate a basic mesh. So just click on generate, and if we select mesh and then generate, yeah, it should generate a basic mesh. So this is the mesh that the program is just automatically going to generate. It doesn't have any settings, and it's not as good for our problem. So to model this problem, we're going to select mesh, right click, and we're going to change the mesh by going under insert and finding face meshing. Once we have that, we want to use this face selection tool. Click on that, click on the surface, and go to geometry down here, click, and then select apply. This will apply a face meshing to this surface. We want to click generate mesh again. And we can see, you may notice a slight difference. The lines, the vertical lines especially, become a bit more straight, but we're not done. So right click again on mesh, and we're going to insert a sizing. And for this sizing, we will use the edge selector, and we're going to want to select both the top and the bottom surfaces. So to do this, you're going to want to hold Control on your keyboard, select one, and then select the other, and go ahead and click apply. Now the settings that we want to use, we want to change the type to number of divisions, and we can set then the number of divisions to say 50. And then we're going to want to go under capture curvature and select no. This allows us to change the behavior and we can make this a hard requirement for there to be 50 divisions across both of these lines. After that, we can generate the mesh again, and if we select the mesh up here, you can see there are much more rows in our mesh, but this isn't perfect yet. So we want to right click again, insert another sizing, use the edge selection tool, and this time we can do the inlet. Click apply. We want to change the type to number of divisions again, and for this one we're going to do 60. And we are going to not capture curvature, set this to hard, and we do want a bias type for this. So go ahead and select this first bias. It's going to be this row, but you can see there's like a few underscores, 3, 2, 1. And we have to define a bias factor. For this problem, we'll use 70. And you can see that these chunks at the top are much bigger, and at the bottom we have very fine chunks. I believe we can zoom in and you can see that. And we're going to want to generate the mesh again. So now you can see we have many cells down here. And now we want to make it symmetrical. So to do that, we're going to select mesh, right click, insert another sizing. This time select the opposite edge, click apply, and we're going to do mostly the same settings as we did for the other side. So set number of divisions to 50. No, that was 60. We're not going to capture curvature. Set the behavior to hard. There's going to be that same bias, and the factor will be 70. However, if you look, this isn't right. We have the chunks at the bottom and the smaller pieces at the top. So to fix this, select reverse bias, select the edge, and click apply. You'll see the bigger chunks have moved to the top. And at this point, we can generate the mesh again. Now if we look at the mesh, it's a nice symmetrical shape. This is a good mesh that we want to use for this problem. The last thing we want to do before moving on is apply some names to these different areas of the surface so that we can better find them when we're making our solutions. So we can use the face selector to select this face, right click, and create name section. For this whole surface, we'll call it airflow. We'll use the edge selector now. This coming from the left, create name selection, and this is going to be our inlet, which will make this our outlet. At the bottom here is going to be our flat plate, and this top zone we can call the far field pressure. Okay, and always before moving on, you want to save your project, and we can exit. So this lightning bolt is not what we want to see. We would like a green check mark. This is very normal though, so you just want to right click and update it, and this should create a check mark, and then you'll see setup is going to be ready, and then we're going to go to setup and continue from there. But we'll give the computer a minute. Okay, it's done. So you just want to click on setup, double click. It's going to open this menu. We always want to use double precision. I am using the student version of Fluent, so I'm only able to use 4 cores of my processor. If you set it above, you will have a problem. If you want to be safe, you can always just use 1. If you don't know how powerful your computer is, or if you don't have 4 cores, we're limited to 2D also because of the student version, but this is a 2D problem, so that's okay. And we just want to start. Wait for it to load in. All right, now we see kind of this flow going on. This looks very pretty. The first thing we like to do is run a check. This will tell us if there's any errors. At the bottom you can see there's done, so that tells me that we're fine. We can also report quality. No errors occurred. You would see them in red if there were, so this is good. We want to make sure that time is steady, planar. These settings, how it is default, are good. We're going to go under model. And for this problem, it is a laminar flow problem. So we need to change the viscous equations that the computer is going to use to solve it from whatever the default is to laminar. Select OK. Next, we want to move under materials. And this is where we can edit our values for air. We're going to be using air, double click it. So here are some default values for air that it has. However, the question says to use 1.2, I believe. Yeah, 1.2 kilograms per meter cubed, which this is. And then the viscosity is 1.8 times 10 to the negative 5. So this is just going to be, hello, come on, 8. And we are good on that front. So we're going to click change/create before moving on so that it saves our changes, and we can close that. Next, we want to move under boundary conditions. We want to go to the inlet, and we're going to set the magnitude of the velocity coming in to 2 meters per second. And this setting is also good, normal to the boundary. Normal to the boundary is parallel to the plate. So that's how the question wants it. At the bottom here, under type, you can see the program has automatically selected that it's the velocity inlet. These are the names that we set for things, and we can go ahead and check that it recognizes it the right way. So we can see in the diagram the inlet and outlet are correct. Interior airflow, that's recognized as the interior. The flat plate is a wall, and the far field pressure is set to pressure far field, but we want it to be a symmetry for this problem. And this name is still fine to keep, but now the type is symmetry. Next, we want to move to under solution. We're going to find methods. The scheme should be simple. we're going to use least square cell based, and second order for both of these are both good. So these settings are good now. Next we want to move to monitors. Where's monitors? Here. Sorry if you guys were staring at it and I couldn't find it, I'm blind. And then we want to go to residual. Here's where we can set how accurate the computer will solve it to be. Number of iterations, 1,000 is good. For absolute criteria, we're gonna be checking for convergence, and we just want to make sure that these three equations converge all to 0 and under a certain number of iterations. So to make this more accurate, we can't set the absolute criteria exactly to 0, but we can set it to far less than 0. So, or not less than 0, what am I talking about? As close to 0 as we can be. So a good one to use is 1 times 10 to the negative 7. That'll just be a decent bit more accurate, and we can select OK. Then we're going to want to go under initialization. It should be set to standard. We're going to compute from the inlet. We're going to set, the x velocity is set to 2, which is good. And these settings are good. We can select initialize. Now we can go ahead and run the calculation. Under number of iterations, we're going to set this to 1,000,000. It should definitely converge within 1,000,000 iterations. And now we're ready to calculate. This is the fun part. We click calculate, and it's going to draw these graphs. We get to watch it, so cool, and we get to watch our solutions. They are converging. It says done, but my computer is clearly thinking about something. Oh no, did we crash? Oh, calculation complete. Okay. Plot twist. So that's great. Under results, now we can model some of those things that the question was asking us for. We want to do a plot, XY plot. Or first, let's do graphics. Let's do the contour plot. This is part 1A of the question. We're going to do contours of velocity. So this is the contours of velocity graph. It's hard to see, but if you zoom in, you can see that these lower velocities are happening all across the bottom. That's due to the no-slip condition. And as we get closer to the top, we approach that free stream velocity, and then we're at roughly 2 the entire time everywhere else. So that tells me that that is correct. We can also, the question asks for vectors. We can open up vectors, and it's already set to velocity, so we can display that. And this will show us the direction that the flow is moving in, but it's very much the same thing, and it also shows the magnitude with the vectors. So we have almost 0 basically here with the no slip condition, and the vectors not only change color but change size. So that's a nice representation of the flow. Now we can go under plots and create that XY plot that I was so eager to create. I almost skipped a step. For the y-axis, we want to set this to wall fluxes, and we can plot the wall shear stress. That is the correct variable that we want. We're going to want this and eventually the skin friction coefficient. And for the x, it's going to be a direction vector, and for the surface, we're going to select that we want it to calculate it along the flat plate. Save and plot, and here's a beautiful graph of the wall shear stress. Next, we'll do the skin friction coefficient. We don't have to change any other settings. We can plot that. Very similar looking graphs. Now we're going to find the drag coefficient, which was part 1D, so we are going to be skipping around a little bit. What I like to do for this one is just use this handy search function, search drag, click the first option, and then we do not want to report the file. We want to report over the flat plate. The drag coefficient is selected, and we want to print to console so that we can see it show up down here. Drag coefficient is not a local variable, so it's going to be global. It's going to be the same for the entire thing. I click OK, it should run that. Where is it going? We want to click compute, not OK. That's my mistake. So here is CD for the flat plate coefficient of drag. At this point, this is all that we need from this section. We can save the project. We always want to save before we move on and close. It's saving. I think it's taking longer because I'm recording. It's not responding. It doesn't feel like going to work today. It's saved, so we close, and we have check marks on setup and solution because we solved it in the setup. But now we can use what's called CFD post. That's the package that will open when we click results and open it. This is another method of modeling our different reports and things. This is still loading in, I believe. Is it? Maybe not. I think we're good. So just so that we can see this, we can create a contour and we can do a pressure since we did velocity last time, and apply. Where's the surface? Hello. We want this on the, it looks like one of these symmetries. Okay, there we go. That looks correct. Now that we can actually see our surface, because it's such a thin horizontal flat plate at the bottom, we couldn't really see it before. We can go ahead and insert a location. So the question asks us to find different things at 35 centimeters and 75 centimeters. We're going to call this line 35. This will be the 35 line. And this is x, y, and z. So the x coordinate is going to be 0.35 and then 0 for the rest is fine. And then the other point is going to also be at 0.35, but it's going to be at 0.5 in height. And we have no z because it's a 2D problem. Hit apply. And we have our 35 line here. We're going to insert another location, line, we'll call it 75. And for this one, we want it at 0.750 and 0.75 is 0.5. Apply. All right. Now that we have our locations, we want to create a chart with this icon. We will call this the 35 chart. Oh, okay. Yeah, 35 chart. And now we have a blank chart to work with. The name of this, what are we finding? The velocity profile. So we'll call this velocity profile at 35 centimeters. Under location, we're going to select the 35 line that we created. Along the x-axis, we want velocity in the u direction. Along the y-axis, we want y, the height. Click apply, and it graphs this velocity profile at 35 centimeters. Next, we'll just do the same thing. We will call it 75 chart. My bad. We will call it velocity profile at 75 centimeters. Select our 75 line. Go to the x-axis, and the settings are going to be the same. We want the velocity in the u direction, and we want the height in y. This is our velocity profile at 75 centimeters. And that's all the question is asking for, I believe. So we have the velocity with the vectors and the pressure contours. We plotted the velocity profile at 35 and 75 centimeters. And it says get the boundary layer thickness at these locations using those. So I'll show you how to do that in a second. Plot the wall shear stress and skin friction along the flat plate we did in the setup and solution section, and we got the drag coefficient also in that section. So to find the boundary layer thickness, we can interpret it from this graph. So what this graph is telling us, across this x, as we increase in x, this is the velocity. So it's 0 at the beginning, and it's slowly increasing until it reaches about 2, it dips over 2, and then it steadies out to 2. And in the y, we have the height of the surface. So kind of imagine we have our flat plate along the bottom here, and this is almost like the air is coming through, and this is telling us how the air is moving. So it's increasing in speed as the height from the flat plate increases, until it reaches free stream velocity, and then it remains like a constant 2. So we can see the boundary layer thickness by finding this intersection at 2 when it first becomes 2 meters per second, and we can estimate the height from here, where we can find the value of this point. And the same thing goes for the 35 chart. So thank you guys for sticking through this recording, and I hope that you enjoyed and maybe learned something, and have a good rest of your day.